Hello and welcome to the first and only video on the FP2 chapter series. On the screen, a quick review of a P4 concept, partial fractions. You don't need to have done P4 partial fractions in order to follow this video, but it will be a big help to you when you come to do the practice questions. Split 1 over r plus 1 into partial fractions. To do that, we need to make an assumption that we can split this with its factors over two separate fractions. Now if this is true, when I put these two fractions back together, then I can find out the values of a and b by comparing coefficients. This is not the only way to do it, but this is the way that I would do it. Multiply everything by the denominator, gives us 1 ar plus a plus br, and then we've got a plus b r plus a must equal 1. Now that means that the constant a must equal 1 and a plus b together must be a 0 because here we've got r and here we do not. So from that I can say that a is equal to 1, a plus b equals 0, and of course putting these two together tells me my final answer is this for a and b. So this thing at the top is equal to 1 over r minus 1 over r plus 1. I hope that is familiar to you, but even if it's not, you can still learn the concepts in this video, which is to use the method of differences to sum finite series. The method of differences can be used to find the sum of a finite series, not an infinite series, only a finite series because it relies on finding both the first term, which is fine, and the last term, which of course you only know for a finite series. Most of the terms in the method completely cancel out. That's the strength, that's how this method works, but you've got to be careful from question to question because it will not always be the same terms that cancel out each time. So the problem-solving part of this method is finding the pattern of how the terms or the bits of the terms cancel out. But first, to be able to apply the method of differences, you must be able to write the general term of your series as the difference of two related expressions. Something like this. So here you've got your general term of your series. If you can write it as a function minus that same function, where you've got r here and not necessarily r plus 1, but r plus a, where a is an integer, then you've got two things of very similar format. One a positive, one a negative. That is the absolute foundation of how this method works. So you must be able to write your series in this format, which is why partial fractions is quite useful in this section. Then you can rewrite your sum that you're trying to find as the sum of the difference of these two things. Why that is so useful is because if you have r equals 1, your first term in your series, and you put that into here, you've got the function evaluated at 1 minus the function evaluated at 2. And then you go to add your second term of the series, where r is equal to 2. And when you do that, you're adding r is 2 in the function, minus r plus 1, that's 3 in the function. And you can see that if you add this term and this term together, the function evaluated at 2 cancels out. Positive here, negative here. And if I keep going and I add the third term of the series, I get f3 minus f at 4. And again, f of 3 here cancels with this one here. So you can see as I keep building terms, every time I add a term, part of it will cancel with something from a different term. And if you keep going, eventually you'll get to r is equal to n. And all the way through this, the first part of your term that you're writing will cancel with the second part of the previous term. So that will cancel with that, and that will cancel with that, and the next one will cancel with this, and if you keep going down, this one you know will cancel with the second part of the previous term, and at the end you've only got this one and this one left, and that's it. And then you can rewrite this thing just as f1 minus f of n plus 1. And these will be two things that you know. When we go through the examples, it'll be a bit easier to see what this means. And we do tend to write it like this rather than what you might expect, f1 minus f2 plus f2 minus f3 like this, rather than one long line. We tend to see it written like this down the page, just because it's not always clear which ones will cancel where, and seeing the pattern of cancelling is a bit easier when it's written vertically. So although you could do it this way, it tends to be written like this, and I think your textbook would probably write it like this. So let's see how this works in an example. It's not uncommon in questions like this for them to get you to show the relationship that you're going to use first, or like we had in the starter question, find it using partial fractions, and then use it to find the thing that you actually want, the sum. So we're going to do that. We're going to show first of all that 4r cubed is equivalent to this expression. And that's actually really difficult doing it that way around, showing that this is equivalent to this. It's actually going to be much easier to start with the complex expression here, simplify it, and show that it will give you this. So that's what I'm going to do. It doesn't matter if you start with the left or the right, unless the question specifies. So we've got r squared, r plus 1 squared, minus r minus 1 squared, r squared. And if I just expand all of that out, we get r squared plus 2r plus 1, minus r squared minus 2r plus 1. We get r to the 4 plus 2r cubed plus r squared, minus r to the 4 plus 2r cubed minus r squared, and you can see that this one cancels with this one cancels with this, and the other two add together to give us our needed 4r cubed. So this is indeed true, we have shown that. Hence, i.e. using this fact, prove by the method of differences that this is true. Now you do know a different way of doing this. We did proof by induction in FP1, so a question often will specify which type of proof it wants. So we have to do this by the method of differences. First thing we need to do is write down that the thing we're trying to prove is very similar to this thing here. I've said very similar to because it is not quite equal. A sneaky little thing to watch out for is the thing that you have shown is equal to something here is not the same as the thing inside the sum. Be careful on this. So what I actually want here is this one, because this is the only one I can actually work with in terms of a difference of two expressions. So I'm going to need the 4 in here, and at the end I will remember that I can write that as this. I can bring that 4 outside if you remember the work on series we did previously, and then I can just divide everything by 4 at the very end. So we'll keep that in mind, but at the moment we have to work with 4r cubed, even though r cubed is what we really want. And that's because that is equal to this. Now, to be very formal about that, I should put all of that in brackets to indicate it is all included in the sum. Now I have to find the pattern of cancelling, so I try r is equal to 1 and see what we get. If we put the first term r equals 1 in here, we get 1 squared, 2 squared, minus 1 squared times 0 squared. And I'm going to write it out like that. 1 squared times 2 squared minus 1 squared times 0 squared. And of course I could evaluate that, but there's no point evaluating this because I know a lot of my terms are going to cancel. I don't want to evaluate things that I don't really need. So I'm not going to evaluate them yet. I'll see what cancels first, and then we'll just evaluate the things that we need at the end. So our second term of the series would be 2 squared times 3 squared minus 2 squared times 1 squared. And you can see here that this first part of the first series term will cancel with the second part of the second series term. So let's see what's going to happen with the next one. We've got 3 squared, 4 squared, minus 3 squared, 2 squared. And we see the same thing happening. The second part of this new term cancels with the first part of the previous term. So I can see that pattern developing. Let's take it all the way down. Let's try n minus 1. That would give us n minus 1 squared, n squared, minus n minus 1 squared, n minus 2 squared. And the pattern was that the second part of the term cancels with the first part of the previous term. So this one will cancel with the part that I can't see. I didn't write inside here with the dot dot dot. Let me cancel some of these. That cancels with that. That cancels with that. This one cancels with one that we didn't write inside here. This one will cancel with the first part of the one before it. And then I've got my last term, r equals n. So that's n squared, n plus 1 squared, minus n squared, n minus 1 squared. And we can see again that the second part of this term cancels with the first part of the previous term. But this part of the term does not cancel, because if it did, it would cancel with the second part of the next term, and there is no next term. Just like this one didn't cancel because there was no previous term. So we end up with this part of the last term and this part of the first term as the only things that haven't cancelled. So my big expression in blue becomes minus 1 squared, 0 squared, which of course is 0, plus n squared, n plus 1 squared. Now I need to remember that that was not really what I wanted. It was very close to it, but not quite, and the 4, as we said, can come outside, and then I can just divide everything by 4, and we get the required result. Like so. So you'll see the same general process every time you do a question like this. First of all, you need to find an expression where you've got the difference of two things, something positive and something negative. Otherwise, when you start adding them together, nothing would cancel. This negative in here is very important to the method. Maybe you'll have an expression given to you. Maybe you'll have one given to you that you have to show is true. Maybe you'll have a partial fractions that you need to find for yourself. Then you need to write out a list. I would recommend at least the first 3, and unless the pattern is very obvious, probably the last 2. This would be my minimum usually to find the pattern, how things cancel. So write those out and then start cancelling things until you can understand what will be left over. In this case we had these 2 bits left over. Put them out, and usually you'll need to combine those and simplify. Possibly at the end you will then have to use your expression that you found to evaluate something with numbers. And we'll do that in the third example. But for now, let's go on to the second example. Using the method of differences, find the sum of this. Write your answer as a single fraction in its simplest form. So here we've got the method specified, method of differences, but we don't have an expression that is a difference between two things. We're going to need to make this into a difference. And this is a partial fractions question. We did this at the beginning. In the starter question, we found that this becomes 1 over r minus 1 over r plus 1. So we've already done the prep work for this question. So the sum here becomes 1 over r minus 1 over r plus 1. Then I find my first term, which would be 1 over 1 minus 1 over 2. The second term would be 1 over 2 minus 1 over 3. You can see it's quite a simple cancelling here. You can see what's going to happen. 1 over 3 minus 1 over 4. Maybe we don't need 2 terms at the end. Maybe we only need the last one. We can see that as you add the next term, the first part of that cancels with the second part of the previous term. So that cancels with that. that cancels with that. The next part we can't see cancels with this part. This one will cancel with the second part of the one we can't see here. And at the very end, this won't cancel because it would need another term underneath to cancel with that. So we've got this bit left, and we've got the very first bit left. So this becomes a 1 minus 1 over n plus 1. And if we combine those, we get n plus 1 over n plus 1 minus 1 over n plus 1, which just gives us n over n plus 1. So I hope you can see the same sort of idea. First, partial fractions, which we did in the starter question, to get an expression of a difference. Then make your list, find your pattern of cancelling, see what's left over, simplify. Same idea in the next one, although it's a bit of a more involved question. Using the method of differences, prove that this equals this, where a and b are constants to be found. Hence, that means use this, find the value of this to 5 decimal places. So we're going to do this in 3 fairly chunky parts. First of all, I need to make a difference out of this. And again, partial fractions is going to come in here. So we've got 2 over r plus 1, r plus 3 is equal to a over r plus 1 plus b over r plus 3. Combining these would give me a r plus 3 plus b r plus 1, multiply everything by r plus 1, r plus 3, gives me a 2 here. Then we've got ar plus br plus 3a plus b has to equal 2. And again, I have no r terms over here, so a plus b has to equal 0. And 3a plus b must equal 2. If I combine these two together, I can see a plus b equals 0. If I use an a plus b is equal to 0 in here, I end up with a 2a left over. So I've got 2a must equal 2. So a must equal 1, and then b must equal minus 1. So my fractions become 1 over r plus 1 minus 1 over r plus 3, and here is the all-important minus, giving us the difference of 2 parts to this expression. So I've got that on the next screen up here. This is what we're going to use. The next part is prove that this thing, which we can change to this, gives us this. We need to find the values of a and b. So this is our method of differences. We've got the sum, r is equal to 1 to n, no longer of this thing, but of these two things here. So we've got 1 over r plus 1 minus 1 over r plus 3. Then we go ahead and write out our list. When r is equal to 1, we've got 1 over 2 minus 1 over 4. When r is equal to 2, we've got 1 over 3 minus 1 over 5. And you can see straight away nothing cancels there. But don't panic, keep going. It's not always the first 2 terms that will start to cancel. So r is equal to 3 gives us 1 over 4, there we go, minus 1 over 6. So we can see the second part of the first series term cancels with the first part of the third series term. So that cancels with that. Let's do one more just to make sure we've got this right. We've got 1 over 5 minus 1 over 7. So the term I'm adding, the new term of the series that I'm adding, the first part of that cancels with the second part 2 terms earlier. So as I write the next one out, that would cancel with this. And the one after that would cancel with this, and so on and so on. These two will never cancel, because that would have cancelled with this one here, and it isn't there. So what I'm going to do is write 2 more, dot 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 here. So the second last term, r equals n minus 1, would give 1 over n minus 1 over n plus 2. And the last term, r is equal to n, would give 1 over n plus 1 minus 1 over n plus 3. And each of these two, as we write the next term, we saw the first part cancelled 2 bits earlier. So this one here, the first part, is going to cancel with 2 terms earlier, and there are 2 terms earlier somewhere in here. And of course all these bits in here have also cancelled with this and this. Then the last one that we wrote, the first part of that will cancel with 2 terms earlier, and there are 2 terms earlier. But this one here will not cancel because it would need 2 more terms after it in order to cancel, and same with this one. So we've got these 2 on the end here, and these 2 on the start here that will not cancel with anything. So these are the terms that we need. We've got 1 over 2 plus 1 over 3 minus 1 over n plus 2 minus 1 over n plus 3. And we need to simplify all of this into this. So it's just a bit of algebra now. We've got 5 over 6 there. So if I multiply everything to get a common denominator, 5 n plus 2 n plus 3 minus 6 n plus 3 minus 6 n plus 2, and that all comes from making the denominator the lowest common multiple between all of those denominators. Expanding that out, we get 5n squared, and then we would have 5n, so that's 25n, and 6, so that becomes 30, minus 6n minus 18, minus 6n minus 12, and we should find they all cancel, giving us that over this. And then 25n minus the 12n here gives us 13n, and we can take out the n as a common factor, giving us a 5n plus 13 all over these 2 here, and the 6, where a is seen to be a 5 and b is seen to be 13. And now we know that this thing is equal to this thing with these 2 constants in place. We need to use that now to find the value of this. But that's all of the work on the method of differences here on this page. We changed this into an expression of a difference, made our list, found the pattern of cancelling, found which ones were left over, put them together and simplified them. So let's finish this off. Here is the expression up here, the 5 and the 13. We need to find this. So to find the sum from 21 to 30, you need to remember your work on series. That's the sum from 1 to 30 minus the sum from 1 to 20. I was a little bit lazy there, I didn't write out the actual expression, but you can see what I mean. So to get 1 to 30, we need 30 as our n here, and the a and the b, 5 and 13 respectively. So we're going to have 30 times 5 times 30 plus 13 divided by 6 times 30 plus 2 times 30 plus 3 minus the same thing, but now n is 20, 20 here, 5 here, 13 here, 20, 5 times 20 minus 13 all over 6 times 20 plus 2 times 20 plus 3. And if you put all of that onto your calculator, you should find the answer 665 over 24288, and in decimal form that is 0.027379777 ... and to 5 decimal places 0.02738, which is the final answer the question wants. So I hope that's enough. Let me just quickly recap one last time. Make sure you can split this into an expression of a difference. Write out the list of your terms. The first 3 and the last 2 are usually a good starting point. Sometimes you don't need quite as many as that. Sometimes it's good to have a few more. Then see which ones cancel, find the pattern, find which ones don't cancel, put them together, simplify. And you can practice these ideas with all of the questions from exercise 2A and straight into the chapter 2 review exercise. Maybe I'll see you for complex numbers in chapter 3.